We first talked about eigenvalues back in tape 14. If you do not remember eigenvalues and eigenvectors at all, you probably need to go back and review that tape before continuing. I will pick up where we left off on tape 14 and show you a little bit more about calculating eigenvalues and eigenvectors. In particular, in today's class, I will show you an example in which one eigenvalue has two eigenvectors. And we'll talk about what can possibly happen with eigenvalues of multiplicity greater than 1. Let's start with a little bit of a review. Remember, lambda was used to denote an eigenvalue. And we wanted to find a lambda such that Ax is equal to lambda x for for lambda, a constant. So what we're saying is there a constant lambda such that matrix A times column vector x is equal to a scalar lambda times the column vector x. So this is what we were looking for. Well, remember what we did? We subtracted ax from both sides to get lambda x minus ax would equal to 0. We introduced the I, lambda I x minus ax is equal to 0. Factored out the x, lambda I minus a times x is equal to 0. And we talked about the determinant. Now, I'm not going back and review all that since it's in tape 14, but we came up with the determinant of lambda I minus a equal to 0 is the characteristic equation of matrix A. And the roots of the determinant of lambda I minus a equal to 0 are the eigenvalues. So that's basically what we said in tape 14. Now let's look at an example. Let's find the eigenvalues and the corresponding eigenvectors for A equal to the matrix 3, 2, negative 3, negative 3, negative 4, 9, negative 1, negative 2, 5. What we want to do is to find lambda such that the determinant of lambda I minus a is equal to 0. And this is called the characteristic equation of matrix A. So we want to find lambda such that the determinant of lambda I minus a is equal to 0. And lambda will be the eigenvalue. We can let derive do the dirty work for us. So I went to derive, and I authored matrix A. So you'll see this is the same matrix that I gave you. This is A. Then I authored the identity matrix I. Then I did lambda I minus A. So this is lambda times I minus matrix A. And I said simplify. And we have lambda minus 3, negative 2, 3, 3, lambda plus 4, negative 9, 1, 2, lambda minus 5. So this was a matrix, lambda I minus A. Then I authored the determinant of number 4. So I just said author expression, determinant of number 4. And I've got lambda cubed minus 4 lambda squared plus 4 lambda. So this is the determinant of lambda I minus A, when I told it to simplify. I set the characteristic equation, or set the determinant equals 0 to get the characteristic equation. So I have lambda cubed minus 4 lambda squared plus 4 lambda is equal to 0. And then I author solve number 7, comma, lambda. So I expression, and I put solve, solve parentheses, number 7, comma, lambda in parentheses. And this is what derive writes. Then I tell it to do basic simplification, and I get lambda is 0 and lambda is 2. So I get two solutions. Lambda 0, lambda is 2. Now I thought a minute and said, whoa, something is wrong here. I have a cubic equation. With the cubic equation, I should have 3 answers. I only have 2. That means one of these answers is a root of multiplicity 2. So 1 is a repeated root. Well, while I was still on this one, I had derive to graph it. So I went to derive, told it to plot. And derive plotted lambda cubed minus 4 lambda squared plus 4 lambda. So I had derived to plot the characteristic polynomial, and I see my 2 eigenvalues here and here. I see that 0 is a single root, 2 is a repeated root. So 2 is a root of multiplicity 2. So that accounts for my expected 3 answers. 1, 2, 3. So note that lambda equal 2 is a root of multiplicity 2. So the problem said find the eigenvalues and the eigenvectors. So here are the eigenvalues. Now we want to get the eigenvectors. For the eigenvectors, we want to find x such that lambda I minus A times x is equal to 0. And x is your eigenvector. It's a column vector, x. So we want to find x such that lambda I minus a times x is equal to 0. That would be your eigenvector. Well, for lambda equal to 0, I went back to derive, and I told derive to substitute into the expression 4 and replace lambda by 0. So we went to simplify, went down to substitute, and I told derive to go to expression 4, replace lambda with 0. And this is the response I get. Notice everywhere I had lambda, just put in 0. Then I said simplify. Well, 0 minus 3 is negative 3, negative 2, 3. 3, 0 plus 4 is 4, negative 9, and so forth. Then I told derive to row reduce it. So I went to author, expression, and put row reduce, number 11, simplify, and you can see the response. So now we're ready to solve the equation. So I can go back. I have lambda I minus a, when I row reduce it, is 1, 0, 1, 0, 1, negative 3, 0, 0, 0. So that's lambda I minus a in row echelon form, times the x vector, x, y, z, is equal to 0, the 0 vector. Well, solving, I can see x plus z is equal to 0, y minus 3z is equal to 0, and of course across the bottom I get 0 is equal to 0. Well, if x plus z is equal to 0, that means x is the opposite of z. If y minus 3z is equal to 0, that means y is 3z. So, if I let z equal to 1, then I would have y is equal to 3 and x is negative 1. So one value of x would be negative 1, 3, 1. Or we say that negative 1, 3, 1 is an eigenvector corresponding to lambda is equal to 0. Now we're going to worry about lambda equal to 2. So I go back to number 4, go to simplify, substitute, and tell derive to replace lambda by 2. Well, if I put in lambda as 2, then I would have 2 minus 3 is negative 1. So the first row would be negative 1, negative 2, 3. If I replace lambda by 2, the second row would be 3, 6, negative 9. In the third row, would be 1, 2, and 2 minus 5 is negative 3. So I simply went to lambda I minus a, replaced lambda by 2. Then I row reduced number 14 to get this response. So now I use this answer, lambda I minus a times x is equal to 0. So we have 1, 2, negative 3, 0, 0, 0, 0, 0, 0, times vector x, y, z is equal to 0, which gives me x plus 2y minus 3z is equal to 0. And of course this one will give me 0 equal to 0, and 0 is equal to 0. So to get my eigenvectors corresponding to 2, I need to pick values of x, y, and z that make this equation true. So we need to pick values for x, y, and z such that x plus 2y minus 3z is equal to 0. Because I've got to satisfy this system of equations. I'm looking for I'm looking for a column vector x that makes this equation true. Well, column vector x is x, y, z. And when I multiply, I end up with this system. Well, obviously 0 equals 0 is true, so I just have to worry about making the first one true. Well, let's let x equal 0. Now, if x is 0, that means 2y minus 3z is equal to 0. So I can let y equal 3 and z equal to 2, and everything would work. Because we can see 0 plus 2 times 3 is 6, minus 3 times 2 is 6, so 0 plus 6 minus 6 is indeed 0. So one vector would be 0, 3, 2. But I can get a second vector. I could let y be 0. Now if y is 0, that means x minus 3z must be 0. So we could let x equal 3 and z equal to 1. So that would be 3 plus 0 minus 3 is 0, so the equation is true. So I could say a second eigenvector is 3, 0, 1. So we can say that 0, 3, 2 and 3, 0, 1 are eigenvectors corresponding to lambda equal to 2. So we see that lambda equal 2 has 2 eigenvectors. Now right now you're probably thinking, wait now, you could create about as many as you wanted to. You could create more. Well, I'm going to deal with that. And I'm just going to point out that one could easily get 3 eigenvectors. The way you could easily get 3 eigenvectors would be let x equals 0, then y equals 0, then z equals 0. Now we let x equals 0 and y equals 0, then I quit when I got 2. Well, why didn't I go on and let z be 0 and get a third one? Well, the reason is the set of 3 eigenvectors will be dependent. So if I create the 3 eigenvectors by letting x equals 0, y equals 0, and z equals 0, then the set of 3 will be dependent. Any 2 of the 3 will be independent. So you didn't have to do it the same way I did, but if you do 3 of them, you will find that all 3 of them are dependent, but any 2 will be independent. Well, let's show that 0, 3, 2, 3, 0, 1. Now these are the 2 I did, and negative 2, 1, 0 is dependent. So this set of vectors is dependent. Well, you might be saying, well, where did you get negative 2, 1, 0? I'm glad you asked that, because let's go back to here and let z equal to 0. With z is equal to 0, that means x plus 2y is equal to 0. X is equal to a negative 2y. So if I let y be 1, x would be a negative 2. So I have a negative 2, 1, 0. So that's where the negative 2, 1, 0 came from, by letting z be 0 that we talked about here. And what I said was that the set of 3 would be dependent. Well, I'm going to show you that the set 0, 3, 2, 3, 0, 1, negative 2, 1, 0 is dependent. I'll leave it to you to show that any 2 are independent. Or maybe I might show you these 2 are independent. But first, I want to show you that 0, 3, 2, 3, 0, 1, negative 2, 1, 0 is dependent. Well, to show that it's dependent, I must show that I can find C1, C2, and C3, not all 0, such that the linear combination of the set with the constants gives 0. So I must find C1, C2, C3, not all 0, such that C1 times the first vector plus C2 times the second vector plus C3 times the third vector is equal to 0. Now we've covered dependent, independent before, so I'm just doing the same thing. Well, if we go through and find our equations, that would be 0C1 plus 3C2 minus 2C3 is equal to 0. This would be 3C1 plus 0C2 plus C3 is equal to 0. C3 times 1 is plus C3 is equal to 0. This would be 2C1 plus C2 is equal to 0. So what I need to do is to show that I can find at least one non-zero solution. So since I only have to find one non-zero solution, I'm just going to let C1 be 1. If C1 is 1, then that means C2 is negative 2. Well, C2 is negative 2, then that means that C3 would have to equal, and let's see what C3 would have to be. Well, we can look here. If C1 is 1, then C3 has to be negative 3, because that would be 3 times 1 is 3 minus 3 is 0. So we let C1 be 1, C2 be negative 2, and C3 be 3. Now I've got these answers using just these two, so make sure this one works. So 3 times negative 2 is negative 6, minus 2 times negative 3 would be plus 6. Negative 6 plus 6 is 0. So these three make all the equations true. So therefore, dependent. Going to run the tape a little bit long, but maybe I better go ahead and show you that the two that I used are independent. So let's show that the set consisting of the vectors 0, 3, 2 and 3, 0, 1 is independent. Well, to show that it's independent, we would have that C1 times 0, 3, 2 plus C2 times 3, 0, 1 is equal to 0. Or I have 3 C1. Well, this would be 0. Let me back up. This is going to be 0 C1 plus 3 C2 is equal to 0. 3 C1 plus 0 C2 is equal to 0. 2 C1 plus C2 is equal to 0. And I must show you that to show that it's independent, I must show you the only solutions will be for C1 and C2 to be 0. Well, the only way this one can be true, the only way 0 C1 plus 3 C2 can be 0 is for C2 to be 0. The only way 3 C1 plus 0 C2 can be 0 is for C1 to be 0. And of course, if C1 and C2 are 0, the last one is true. So the only solution to this system would be C2 is equal to 0, C3 equals 0. If the only solution would be the 0 value, then we have proven independence. The number of eigenvectors per eigenvalue is always less than or equal to the multiplicity of the eigenvalue. So since 2 had multiplicity of 2, I knew that the most eigenvectors I could find would be 2. Now I don't know that I can find 2. I may only be able to find 1. Notice the number of eigenvectors per eigenvalue is always less than or equal to the multiplicity of the eigenvalue. So if I have an eigenvalue of multiplicity 2, I might find 1 eigenvector, I might find 2. It's either less than or equal to. The set of all eigenvectors of lambda together with 0 is a subspace of n space. So the set of eigenvectors associated with an eigenvalue lambda or corresponding to an eigenvalue lambda together with the 0 vector is the subspace of n space. This subspace is called the eigenspace of lambda. Now let's look at the proof. To prove that something is a subspace, we have to prove that it has an element in it. We have to prove closure with respect to vector addition and scalar multiplication. Clearly the set is not empty because it has 0. Because I said the set of eigenvectors along with 0. So clearly it has 0. Therefore, we must show that the set is closed with respect to vector addition and scalar multiplication. So let's let x1 and x2 be eigenvectors corresponding to lambda. Now by matrix multiplication, I know that A times x1 plus x2 is ax1 plus ax2. Whereas I can see x1 is a column vector, also a column matrix. x1 is a column matrix. I'm multiplying by A. We know that we can distribute multiplication over vector addition or over matrix addition. That's one of the properties of matrices. In fact, we proved it in an earlier tape. Well, if x1 is an eigenvector corresponding to lambda, then ax1 is lambda x1. If x2 is an eigenvector corresponding to lambda, then ax2 is lambda x2. Well, lambda is just a constant, so I can factor out the constant and have lambda times x1 plus x2. Well, this proves the closure, because this says that A times the vector is equal to lambda times the vector, because x1 plus x2 is just a vector, a column vector. Now let's look at scalar multiplication. A times cx1 is equal to c times ax1. That's the associative property of matrix multiplication. But since x1 is an eigenvector corresponding to lambda, ax1 is lambda x1. So I'll simply replace ax1 by lambda x1. Now I can multiply by the c to get lambda times cx1. And that proves that it's closed with respect to scalar multiplication. So we know that the set of all eigenvectors corresponding to an eigenvalue along with 0 form a subspace of n space. Now what we showed you earlier was that 0, 3, 2, 3, 0, 1 is a basis for the eigenspace of lambda equal to 2. So this would be these are the eigenvectors associated with lambda equal to 2. Now there'd be a bunch of them. I mean, another one obviously would be 0, 6, 4, just multiplying by 2. So there'd be a bunch of eigenvectors in here, but this would form the basis. So the eigenspace then would be the set of all linear combinations of these. So that would be the span of 0, 3, 2, 3, 0, 1. Here's just some notation that I'm going to give you, because I will start using these things interchangeably. Since a linear transformation can be defined as TV is equal to AV, one can define eigenvalues in terms of linear transformations. Because remember, you just have TV is equal to AV, and the eigenvalue lambda, that would equal to lambda V. Lambda is called an eigenvalue of the linear transformation T, mapping V into V, if there is a non-zero vector x such that tx is equal to lambda x. So the only difference is rather than using a, we put t, but tx is ax. Now that t is a function of x is matrix A times x. So we're going from a function to multiplication, but we discussed that in the previous tape. The vector x is called the eigenvector of lambda. The set of all eigenvectors of lambda along with 0 is the eigenspace of lambda. So it's exactly the same thing.